Hello and welcome back to Let's Code Physics. In our last episode, we were able to successfully connect a couple of wires and have electrons flow from one wire to another. So we've got the beginnings of a circuit there. Of course, you can't have a real circuit unless everything is connected and it all goes around in a loop. So that's what we're going to look at today. So what I've done for our wires is I've made 4 of them, and they're going to make a rectangle. We have one that is pointing to the right, and it's located at the bottom of the loop. We've got one that's going to be pointing up. It's located on the right side of the loop. We've got one that'll be pointing to the left. That'll be at the top of the loop. And finally, we've got one pointing down, and that'll be over on the left side of the loop. So this thing will be going right, then up, then left, then down, otherwise known as counterclockwise. As before, we're going to be generating electrons within each of these wires, just in the center of the wire, initially with 0 velocity, and then those are going to be acted upon by the electric field pointing in whatever direction the wire is pointing, and being scattered by randomized scattering events based on the resistivity value. So all of our wires currently have the same resistivity value of 1 for right now. So let's run our animation and get a look at it. Okay, and as we saw before, we're going from one wire to another. So once they enter this overlap region, they're able to transfer from one wire to another. And we're getting a pretty good flow of electrons around here. You'd expect there to be about the same number of electrons in each wire. That's about what we're getting. This one seemed a little bit low at first. The average speed takes a second or so to ramp up here, and then it's oscillating around as we get these scattering events. So this is the average speed, average across all the electrons in the direction of the wire at each moment in time. So there is some variation. We're getting a pretty decent average. Looks like right around 1. So what I would expect to see under Ohm's law is that if I double the electric field, I should see about a doubling of the speed, which is basically the current in this case. So let's see what happens if we do that. Let's take our electric field magnitude. Let's double that to 4. So let's see if we get an average speed of about 2. Okay, we definitely ramped up to higher than last time. I think these things are moving a little bit faster. We do have a little bit higher of an average. It's definitely above 1, right? Because 1 is this line right here. It's not quite 2 though it's kind of hard to tell because of all the variation that we're getting. So one change I'd like to make is instead of averaging the speed over just that instant, I'd like to get an average over the entire time, because the speed is supposed to be roughly constant, and you can kind of get an idea that it's noise to the data. So what I'd like to do is change this average speed calculation that we're doing here in the move electrons routine to average it over time. In order to do that, we're going to need to make a few modifications. The first thing we're going to need to do is make this a global variable, average speed. And basically we're going to want to modify that every single frame and not reset it. So we'll start it out at 0 in this case. So this is going to be the speed averaged over the electrons to be averaged over time. And I'll show you what I mean by that in just a second. So we're going to get rid of this part right here. And since this is now a global variable, I don't need to return it anymore. This can just be a function that doesn't return a value, that just modifies that value. And so what we can do, actually, I don't want to average this over the number of electrons, because if I do this, I'm going to keep dividing the previous data by the number of electrons, because basically what we're doing here is we're adding the average speed for each electron, but we're continuing to add based on the for each loop. So every time we go through a loop, we'll be adding another 120 data values. And so if I divide every time, then that's going to be dividing the first 120 by an extra time, and then the next one by an extra time, and then the next one by an extra time, etc. So let's get rid of that part as well. So what I can do then is I don't need to have that equal there anymore because I'm not returning it. So this is now just saying move electrons, not calculate move electrons and store the answer somewhere. And what I can do here is I can take the average speed and divide it by the number of electrons, so that's length of electron underscore list. And I can divide it by the amount of time that I've gone through. And let's put that after the time update because our time is starting at 0, right? So we're moving it forward 1 increment, so we want to avoid a division by 0 in the first frame. I think that takes care... Nope, I need one more. There we go. Nope, I need one more. There we go. Okay. So we've got length of electron list times the time. This parentheses closing up the denominator. This one is closing up the position argument, and this one is closing up the plot command. Cool. Let me check my to-do list to make sure I got everything there that I need. Make a global variable check, set it to 0, outside of move electrons check, remove the average speed from return and equals lines, check, and then divide by the time in the plot. And I forgot that I would also need to divide by the number of electrons there. Okay, let's see if this works. Should work out fine. Uh-oh, we do not have local variable average speed. Oh, right. I may not be calculating average speed here, but I need to tell it, hey, I'm accessing the same average speed. There we go. And the fact that I'm calling it global there indicates I'm referencing the same global variable up here. Although I thought declaring it global would auto-populate down here. I guess not. I'm getting my language is confused. Okay, so you see how the line is much smoother now. We don't have all that jaggedness because we're averaging over the speed. I'm a little bit concerned now though because that is a lot bigger. Oh, you know what? I don't want to divide by the time. I want to divide by the number of iterations that I've gone through. So the number of iterations that I've gone through is going to be time divided by dt. There we go. Oops. Right. So when I divide by time, I'm actually taking velocity, dividing it by time, getting an acceleration. Not that that's not an interesting value, but that's actually not acceleration because it's not change in speed over change in time. It's just a meaningless jumble of variables. So we've got being divided by t divided by dt. So this is going to be the number of iterations. So t divided by dt equals number of iterations. Because in our first iteration, t will equal dt, so that'll be number 1. In our second iteration, t will be equal to 2 times dt, so that'll be number 2, etc. Okay, yes, these values look a lot more reasonable than before. So you notice this thing, it varies a little bit. That variation is eventually going to die away because because each time it adds, it's adding proportionately less because it's got so many more data points beforehand. Now, it is artificially low a little bit because of this initial ramp up, because we take everybody to be at rest at first. But basically that just means it's going to be downshifted by just a little bit. Okay, so my average seems to be right at about 1.5. Yeah, that's pretty much as close to 1.5 as you can get. Yes, everything's moving around in a loop. So let's go back to the previous electric field value, see if we get half of 1.5, roughly. If it doesn't work out, I might see about giving them a randomized velocity at the beginning. Okay, so half of 1.5 is about 0.75, 3/4. We're getting a little bit more than that. I suspect that might be the effect of this initial ramp up here. So let's see if we can drown that out by making the electric field magnitude larger. So let's try going from 5 to 10, see if that gives us a better doubling. Basically, I want to make the effect of this initial ramp up as small as possible, although I suppose that is getting larger with the electric field, isn't it? So with an electric field magnitude of 5, again, is it possible that we're saturating it somehow with the with the scattering events, with the resistivity? That's not what Ohm's law predicts. All right, so let's try doubling this to 10, see if we get 3. Right, so last time we got 1.5. We do get a larger value, but it's not quite there. It's not quite 3. It's definitely not doubled. Okay, so I'll do some tinkering with that off camera to see if I can either figure out what I'm doing wrong in the calculation of the average speed, or if there is, or if I'm oversimplifying the relationship between the average speed and the current, and between the electric field and the voltage. Leaving everything else constant, it should be pretty straightforward. Okay, well, I'll leave that as a mystery for you to tell me in the comments what I'm doing wrong. And as always, you can download this code from the description below and play around with it. Post your results in the comments below, or tweet me at LetsCodePhysics. There is one other thing I wanted to try, and that is to change the resistivity of one of these wires. So right now, all of these wires are identical. They've got the same resistivity, and so they've got the same current flowing through them. They've got basically the same number of electrons and the same speed of the electrons going around them. So it's a pretty uniform circuit in that sense. And okay, let's keep track of the fact that this was at 2 previously. What I want to do is I want to change the resistivity of one of these wires. That's basically the equivalent of taking out one of the wires and replacing it with one that doesn't conduct as well. Maybe it's made of a different material, or it's got more impurities, or maybe it's just got a big honking resistor in the middle of it. So I think I'll do that with the top one. So that's the one here that points to the left, that's up at the high Y value. Let's try or go home. Let's increase that one by a factor of 10. So what we should see now is that it should be harder for the electrons to get through this wire up here. I'm not changing the other 3 wires, I'm only changing this wire up top. Okay, and lo and behold, the electrons are zipping through these wires much faster, but they're going through this wire a lot slower. That produces 2 results. Number one, it means that there's kind of a pileup of electrons in here because there's much less current in this one. So the electrons are not flowing as quickly through here. But the electrons are flowing comparatively faster through here. And so that means there's fewer electrons here and there's more electrons in this part of the circuit. What we also see is that the current, the average speed of the electrons decreased. And so we went from 2 to about 1.5. Now, I don't really have a quick calculation of how much that should have changed by, but it did decrease because basically what we're doing is we're increasing the total resistance of the circuit. I could do the same thing in the bottom wire. So let's say we've got 2 resistors connected by 2 wires. And obviously we've got an invisible battery in there somewhere to create the electric field in the first place. And so what we'll see is electrons piling up in this wire and in this wire, and we'll get fewer of them in the left and right wires because they'll be traveling faster. And lo and behold, our current decreased yet again. So I'm getting better current results by changing the resistivity than I am by changing the electric field today. So, I'm 1 for 2 today. And so basically what that's showing you is how the total resistance of the circuit increases, which is pretty cool. Now, what's unphysical about this is that when I change the resistance of one of these wires, that should also change the electric field magnitude of these wires, because basically when you have these wires connected in series, they should have the same current, again current being different from the average velocity in that you've got a slower velocity here but you've got more electrons, so in series, these are supposed to all have the same current but have a different voltage. I've got that flipped around currently where they have the same voltage but a different current going through them. So what I need to do off camera is a little bit of fiddling with the calculations for the electric field magnitude to where these things end up with different electric fields based on their resistivity and their size, because the size also determines the resistance. But this shows you, what the generic effect is. It definitely decreases the average velocity of the circuit overall. So you think of this as the current of the circuit overall. And then we can think of these as being our different resistors in a circuit. So I'm going to work on that off camera, getting the electric field to adapt based on the resistance of each of these wires, and then we'll have a more accurate circuit that we'll be able to do some experiments with. So thank you so much for watching. I will see you next time. Bye-bye.